to all and welcome to this lecture. We are in module 11, lecture number 3, non-quasi-static modeling. In this lecture, we will discuss about non-quasi-static modeling. From the fundamental point of view, what is non-quasi-static operation, and then how can we model our MOSFET in non-quasi-static operation by preserving the quasi-static modeling what we have done so far. And we also see about the extrinsic parasitic which actually governs the overall operation of the MOSFET. So these are the learning outcomes of this lecture which will help you to differentiate between quasi-static and non-quasi-static MOSFET operation by examining the role of finite carrier transit time during fast signal excitation. Meaning, if your gate voltage or drain voltage is fast varying signal, then how your MOSFET responds. That is comes under non-quasi-static modeling or non-quasi-static operation, which we can say as NQS, and quasi-static says as QS. So let's start with a quick recap. In last lecture, we were talking about transit time, where we said that the transit time is the time taken by the carrier to move from source end to drain end. And in first order, we explained that tau is nothing but total inversion charge divided by IDS. We extracted the transit time for 3 different operations. One is weak inversion, one is strong inversion saturation, and then strong inversion non-saturation. We found that in weak inversion, the transit time is not dependent on the voltage, because in weak inversion, the phenomena is diffusion, whereas in strong inversion, once the carrier moves from the source and come in the channel, it will encounter in the field, right? And that's what the transit time reduces. We found that in all the 3 cases, the transit time is directly proportional to L square. Then we said that in saturation, the transit time, the expected line will be this. This dotted line is an expected transit time, right? Whereas there is a concept of velocity saturation. When we talked about small channel devices, velocity saturation means when the movement means when the carrier entered from the source, and if the channel is so small that carrier velocity is saturated, meaning the time taken by the carrier is L divided by Vd max. Now even if you increase the voltage, the time is fixed because Vd max is fixed. Now the velocity of carrier is not increasing, and hence there is a limitation boundary of transit time. Now let's see what will happen if the input signal is varying so fast. So the non-quasi model breaks down when the input signal changes too fast for the channel charge to respond instantly. In the sense, if you have a gate and for example, you are applying a gate signal with a very high frequency. This is a very common sense that because of very high frequency, the charge will not get enough time to respond back. In the sense, suppose if you go from a very layman definitions of MOSFET operation, you will encounter that when you apply the voltage, first the holes will ripple back, depletion happens, and after that inversion charge comes to the surface, which causes an inversion layer and hence results in current. However, when the input is very high or the input signal variation is very high, then the carrier will not get enough time to respond. This is one thing. Similarly, if you increase VDS with a very high frequency, then what will happen? The carrier will not instantly respond from source to drain, and hence the response of the output is governed by transit time, and this is called non-quasi-static modeling. So we can see how this non-quasi-static modeling extends the quasi-static validity by dividing the channel into multiple small sections. The idea here is, if you have a MOSFET like this, where this is source end and this is drain end, the carrier which is entering here will reach to drain, move from the source. Now, if the gate voltage from the top is changing very rapidly, then the quasi-static assumption, what we have discussed in previous lectures, will fail. And the idea here is, to maintain the quasi-static validity, you divide the whole device in a small subsections in such a way that each section follows the quasi-static operation, and you can model each section, and then by using a continuity equation you can relate all these sections. However, indeed it is true that when you connect those sections like this, then the entering current and the leaving current will be different, and hence there will be a charge pile-up problem. It means the inversion charge will be stored a bit, right? To avoid this problem, we need to take care that the section division or subsection length is infinitely small, and then only the non-quasi-static operation can be mimicked as a quasi-static operation, and we can apply the equations what we have derived so far under quasi-static operation. So in this condition, the current and the charge which will go through this surface will be a function of position as well as time. However, if you remember, in quasi-static operation we said that my current is a function of time, whereas as you are splitting the complete device in multiple sections, then it will be a function of x as well. We need to take one more assumption, that the non-quasi-static model assumes that the device dimension will be much smaller than signal wavelength, such that there is no magnetic field or magnetic effects will be arises, and hence the complete phenomena or complete modeling can be controlled by electrostatic laws. Now let's see how can we connect these two sections using continuity equation. Let us consider a small chunk of inversion charge of length delta x. Here the total charge entering from this side is I plus delta I into t, and after delta x section the total charge leaving at this section is I delta t. So we can simply find out based on conventional continuity equation what is the total charge in that chunk. It is delta q is equals to I plus delta I into t minus I delta t, right? This will give you delta I delta t. So this will be delta t, because over the period of delta t time you are calculating, right? So delta I delta t divided by w into delta x. Now let's see how this continuity equation helps us to connect the subsections what we are making to apply the quasi-static modeling in non-quasi-static operation. Let us consider a small chunk of inversion layer of length delta x. The charge which is entering from the right side is I plus delta I into delta t, and the charge which is leaving from here is I delta t. Thus you will get the total charge which is piled up here in the chunk of inversion length is delta q or delta q I dash is equals to I plus delta I into delta t minus I delta t divided by w into delta x, because you are plotting or getting the charge per unit area. So this will give you delta I delta t divided by w into delta x, and hence we can simply write delta I by delta x is equals to w into delta qi divided by delta t. Now if you consider this delta x is very small, you can simply rewrite a differential equation like this, right? This helps us to understand how the current and the charge is related with respect to position as well as time. Now let us see how we can use this continuity equation to convert our quasi-static model into a non-quasi-static modeling with some boundary conditions and approximations. So for the non-quasi-static analysis, as we assume that the required condition is the channel charge will not respond instantly if the time varying signal input frequency is very, very high. Then for the simplicity and for simplicity of the analytical model, NQS behavior is assumed that we have to make small chunks of subsections of the complete device, and then in each section you need to apply quasi-static modeling approach. For the sake of an example, let us consider strong inversion case. In the strong inversion case, we know how we can write the inversion charge, which is nothing but Qi dash is equals to minus of Cox dash into VGB minus V flat band voltage minus psi s minus gamma root psi s. So this is I have written for DC. However, for time varying signal or time varying charge, you can write in terms of minus Cox VGB, which is a function of time, V flat band voltage minus phi naught minus VCB. Here the VCB is the voltage between source and drain, and hence it will be a function of x and t, minus gamma is a body factor, and this is again a surface potential. So this is the one equation which we can use in our basic current equation, which is again, as we are considering strong inversion, we can simply write a drift current equation as Ixt into is equals to mu into W into minus of Qi into delta VCB divided by delta x. That is what we have considered when we were talking about DC analysis, and that is the mean that it is not a function of x and t. Now when you write for quasi-static analysis where the input signal varies so fast, then you can rewrite this equation as this, and we just now derived the continuity equation where you can relate this current as well as the charge, and hence find the continuity of this charge and current to solve for non-quasi-static model. But to solve these equations or the set of equations, we need boundary conditions. Let us consider in the same case where we are taking the MOSFET here and applying the VDD, which is very high such that the saturation operation is taken place. You are in strong inversion and you are in deep saturation, meaning even VG will go to its maximum value, you will be in saturation. That is the condition we are taking. Now every node voltage is fixed, that is VD, VB, only VG is varying. Sorry, this is VB and this is VS. Only VG is varying, and we will see what will happen if VG varies abruptly. In the sense, in previous lecture we saw that what will happen if V will be varied as a ramp function, slowly varying function. However, here the voltage what we are applying is abruptly changing, right? Because of this abrupt change in the voltage, how my charge carrier in the channel will respond. This can be solved by the previous defined these set of equations. Now let's talk about the boundary condition. First is at time t equals to 0, the voltage is 0 because it's a step, right? So you can consider at time t equals to 0 minus, the voltage is 0. If the voltage is 0, it means in the channel there is no charge, right? Meaning the channel is empty. Channel is empty at t equals to 0 minus. But when the voltage suddenly changes at t equals to 0 plus, what will happen? The gate voltage rises up. In response, the channel charge should respond, but it will not respond immediately because it requires some time to respond in terms of current. But if we only talked about charge, then what will happen? If the gate voltage changes here, it means there is a change in gate charge. The change in gate charge will respond in change in the charge at the source side, meaning there will be a source, there will be a stream of electron entered to the source immediately. That is what at x is equals to 0, or you can see x is equals to 0 plus, means just at the source at time t, when the voltage comes, right, the inversion charge will appear. However, this will not give you the current because this charge is present only at the source side now. It requires some time to move from source side to drain side. That is what is called delay time. We can see from this graph that, let us consider the source, the carrier entered at the source and it traveled a distance xa, right? This is L. Here my drain is, right? So when carrier traveled a distance xa in time ta, right, at that moment the charges are only available near the source here, and that was counterbalanced by the gate charge. Now, as you have proper polarity connected in the MOSFET, the charges will move along the drain, and after time TB, TC or TD, ultimately it will reach to drain. That is the point where the drain current starts, right? So now the current will start slowly. This is called delay time. Okay. Now the way the drain current starts slowly, again the drain current will not abruptly settled into steady state. It requires some time, right? And that is what tau naught plus TD, right? So ultimately at time t equals to infinity, the current will reach to steady state. Now let's see what will happen if you change the rise time of the input. So instead of taking step to understand this concept again in a different way, we are taking a ramp function with different rise times. So the setup here for the device is same. Now what we are doing, we are taking a ramp function to understand the phenomena in terms of how charge and the current respond into the device when the voltage is changing, right? So again we are considering the change in the voltage is slow enough such that quasi-static phenomena holds good. Now how this will respond? Again, make a picture in your mind that this is your source and from where the carrier enters, and this will give you a current, that is source current, and from here the carrier leaves the drain and ultimately it will give rise to a drain current. The drain current and the source current dimension is opposite, and in our quasi-static analysis we considered that all the current dimensions are inward. Following those assumptions, let's see what happens when you slowly increase the input. When the input rises slowly, then till Vt, till threshold voltage, there is no current. But the moment you increase the input voltage beyond Vt, then the gate charges changes, right? Because you are increasing Vg. When you increase Vg, the gate charges will change. The change in the gate charge can be counterbalanced by the change in source charge or near the source, and hence the source current immediately rises like this, correct? So this is minus S. As I said, the carriers are entering in the source and hence the current will leave outward the source, right? This is Is, but we are taking all the direction of current inward. So inward direction is what? Minus S. So the minus S will increases. Now at the same time, the gate charge is counterbalanced by the source charge. Till this point, the carrier which is entered at the source does not reach to the drain, right? And hence the gate current and the body current is counterbalancing to each other and causing a source current to rise, which is minus Is. Now beyond a point at T2, when the carrier reaches the drain end, then what will happen? The change in the source current or the change in the gate current is now negligible, right? Or you can say the change in the gate charge now is counterbalanced by the change in the drain charge, which will give you the drain current. That is what the drain current is rises up. At the same time, this is balanced by the increase in the source current. Now, after some time, they both will reach to steady state. But still, if you see at this point T3, till this point the steady state does not reach, meaning the carrier takes some time to readjust itself before reaching the steady state, and hence there is a current which is minus Is greater than Id at this stage, and after some time they will reach the steady state value and become equal, correct? So this is the operation which is happening back end when you apply the voltage in the MOSFET. Now what will happen if you increase the rise time? So instead of this voltage, what will happen if you suddenly increase the rise time? That is what we are going towards non-quasi-static modeling, right? So if you increase the voltage, or you can say delta V divided by delta T suddenly increase, meaning if I go through the equation, you remember I is equals to delta Q by delta V into delta V by delta T. If you increase this part, the current will suddenly increase. So the same phenomena what we discussed so far for this case is simply applicable for this case. However, the difference is the gate current does not get, or the gate current is not getting enough time to settle down, and the value of peak gate current and source current are equal, and this period, which is delay time, is approximately equal to the time where steady state reach, right? So you can get the higher current in response to the high frequency signal. Now this can be limited in short channel devices when the velocity saturation occur. So ultimately, if the device dimension is small enough, then the velocity saturation phenomena occur, and hence this all delay time is limited by Vd max. Okay. Now after this, quasi-static and non-quasi-static operation of the devices, let's discuss about the extrinsic part of the MOSFET. So far, if you remember, we were discussing about only intrinsic part of the carrier, only intrinsic part of the MOSFET. We said that we are considering the intrinsic part of the MOSFET, which is responsible for the basic operation of the MOSFET. The intrinsic part comprises inversion charge, bulk charge, gate charge, and substrate or body charge or oxide charge. However, the overall operation of the MOSFET, when you mount this MOSFET or put the MOSFET in the circuits, that overall MOSFET operation will be limited by its extrinsic effects. That extrinsic effects or extra effects is called parasitics. In general, the extrinsic part exists mainly to connect the intrinsic transistor to the other devices in an integrated circuit. Meaning, when you are discussing about the MOSFET and the models, ultimately you are going to put in the circuit, and when you put in the circuit, you do have some connections. In the connections, there are basically parasitic resistances and parasitic capacitances comes into picture, which will ultimately limit your operation of the MOSFET. Now, what is extrinsic capacitances? You can simply say the charge storing capacity in the extrinsic part of the MOSFET is commonly modeled as a capacitances. Like if I write the equation for change in the current because of the intrinsic part of the MOSFET, then this can be written as dq by dt, which is nothing but a reflection of change in the charge. This charge can be the bulk charge or the inversion charge or so, and I can rewrite this equation as dq by dv into dv by dt, where dq by dv is nothing but what? Incremental change in capacitance, and hence the extrinsic environment of the intrinsic transistor can be modeled in terms of resistances or capacitances. Now, let's see a picture of MOSFET. In the sense, this is a bit scary picture which shows you all the possible components in terms of extrinsic as well as intrinsic transistor. If you see closely, this is the transistor what we have discussed so far. This yellow one, this region is source. This region is drain. The region here is overlap, right? This is the width direction, and this is the gate. So please try to understand the 3D geometry of the device. So this is the gate and this is the oxide. If you closely look into the structure, due to internal characteristics as well as due to external connections, we do have parasitic resistances and capacitances. Let's discuss one by one. So we need to reshuffle this slide again and again to discuss the components present here. I'll give you brief idea about these capacitances and resistances. The first is overlap capacitances. If you see here that there is an overlap, we have discussed in our MOSFET structure that this is source, this is drain, but the source and drain structure does have overlap, right? And when you make an oxide like this, correct, this is an oxide, so there is a small overlap present here, and because of this overlap there is a capacitance which is dependent on width, right? Because along the width you have overlap, correct? So this is C overlap. Here in this structure we can say CGD1 and CGS1 is an overlap capacitances. You understand? Because here you have a metal plate, here you have a semiconductor plate which is separated by an oxide. That is what this is, overlap capacitance. The next is fringing capacitance. We have discussed about the fringing capacitance when we were discussing about narrow width effect. So this is the gate where the electric field lines are not exactly parallel. Some field lines are like this. This is called fringe lines. Because of these fringing lines, there will be a capacitance. If you remember, we have discussed that the effective threshold voltage in case of narrow width device is V flat band voltage plus phi naught minus QB divided by COX to cap. We said that the capacitance in the narrow width device will increase because of fringing effect. That is what it's called, a fringing capacitance. So in this structure, we can simply say these capacitances like CGD-E2 and CGS-E2 are fringing capacitance. You can see from this side. So this is the fringing capacitance. The third one is gate to body capacitance, which is simple as we have already discussed when we were discussing about two terminal structure, because you have gate at this side and body terminal at this side. So this is gate to body capacitance. We have discussed a lot about gate to body capacitance in terms of CGB dash, right? That is also an extrinsic part of the MOSFET. In the MOSFET itself, the gate to body capacitance dependent upon the region of operation. If it is in cutoff region, meaning you are applying the voltage such a way that there is no depletion and inversion, and hence CGB can be given as COX into W into L, the overall capacitance, right? When you apply and operate in a linear region, it will divide half-half. And when you apply in inversion region, it will be 2 by 3 into COX into WL at the source side and 1 by 3 into COX into W at the drain side. Again, this is a layman calculation which gives you these values. Next is junction capacitance. We have discussed about these junctions as well, that we said that if you have a MOSFET like this is N plus this is N plus, and here there will be a junction because the body is p type. In general, we keep this N plus to a positive voltage and body to either ground or negative voltage, and hence this junction, this PN junction becomes reverse bias. And we know when a PN junction becomes a reverse bias, then the expansion in the depletion region causes a capacitance, a voltage controlled capacitor. That is what these diodes can be represented by a capacitor, which is nothing but a voltage controlled capacitor. So these are the junction capacitors. Next is contact related capacitors. What happens is when you make a contacts to source, to gate and to drain, then there will be a capacitor between contacts. Like these are the contact capacitors, right? They form between drain and source. There are also capacitors which forms between gate and drain, gate and source, right? In addition to this, we have body substrate capacitance. So when we go for some twin tub process or well process, what we do is we take a substrate. In the substrate, we make a well like N well and P well, right? To design a transistors like that. Let's say this is P plus, this is P plus. So here, this and this forms a body capacitor, because again it will be a junction, and hence there will be a body or substrate capacitance comes into picture, which can be represented as CBB dash, right? In addition, we do have inner fringing capacitance. In short channel devices, we said that when you reduce down the dimensions, then the field lines will see this side of the source and the drain as another one part of or one plate of capacitor, and this is another plate of the capacitor, and hence they form a inner fringing capacitors, right? In addition to the capacitors, we do have some extrinsic resistances, which plays an important role to limit the operation of MOSFET, out of which one possible extrinsic resistance in terms of source and drain we have already discussed when we were discussing about the impact of source drain resistance in current. We saw that the current is affected by 1 over 1 plus beta R into VGS minus VT, and beta R was nothing but W by L into COX dash into RS plus RD. It means the source and drain pad resistances significantly influences your current flowing in the circuit, right? You can simply go back and see this is nothing but a semiconductor, and the semiconductor does have resistance, because the resistivity or the conductivity of the semiconductor can be defined as N into Q into mu, right? Based on that, you can find out the resistivity and the resistance. So if in the drain and source pad, so in the drain and the source pad, we do have resistances which limits the overall performance. We also have gate resistance. The gate resistance becomes very important when you talked about high frequency RF applications, transient applications, right? Even when DC gate current is negligible, right? So the gate current, to understand the gate resistance, you first see the gate structure. In general, the gate is made up like this, where we do have salicide gate and we do have poly gate. Here is the gate contact, right? So ultimately, when you apply the voltage, what will happen? The current will flow first in this direction and then it will go vertically. Because of capacitive shunting effect, what will happen? The current is, because now because of the capacitive shunting effect, ultimately what happens, this current is no longer uniform, meaning if I connect the gate here, the current will go this side, but the vertical current direction will be non-uniform. That's you can see from this figure. If you are applying a contact here, the current should go in this direction, like in the salicylate gate, and then it will go in vertical direction, correct? But this resistance of the gate is a distributed network, or you can consider as a distributed resistance network. Because of that, what happens is the vertical direction current is different. This phenomena is called current crowding. One of the possible solutions to avoid this current crowding is you can connect the metal gate from both the sides, right? From this side and that side. So we can simply say that the gate resistance significantly influences the overall performance of the MOSFET. Now we do have similarly substrate body resistances. As we have seen already in the MOSFET, you have p-type body, and when we were discussing about JIDL, when we are discussing about drain to body current, we said that because of this substrate current, because of this substrate resistance, there is a significant potential drop and there will be a intrinsic BJT operation starts, and we were discussing about the snapback action. That is what due to the substrate resistances. Now these resistances and capacitances are highly temperature dependent. If you tune the temperature, then not only the intrinsic part of the MOSFET is disturbed, whereas the resistances which is provided by the external part is also influenced. Like a commonly used power law model for the resistance is this, where TR is the room temperature, right, and KR is a fitting parameter. In general, we can use a linear temperature model also, where CR is a fitting parameter. So this says that by changing the temperature, not only the intrinsic part of the transistor changes, however, the extrinsic part is also changes. Now, it is not easy to capture all these resistances and capacitances when you are operating or using this device in circuit simulations, or in hands-on calculation you require some simple models. That is what we can go for a simplified model, where we define all four terminals, which is nothing but gate, source, body and drain, and what we do is we find out the all possible resistances between drain and gate, and we connect like, and what we do is we find the equivalent resistance connected between these terminals and also the equivalent capacitances connected between these terminals. That is what we try to incorporate all possible resistances in one equivalent resistance, correct? Similarly, all possible capacitance effect between these two terminals can be shown by a single capacitance, let's say CGSE, correct? This is an intrinsic part of the MOSFET. So let me summarize this lecture. In this lecture, we have discussed about the non-quasi-static phenomena and said that how we can preserve the quasi-static model by splitting the device in multiple sections and apply the quasi-static modeling in each section with some proper boundary conditions. We have said that when you change the input voltage suddenly, then the charge will not respond suddenly. It will take some time. That was defined as delay time TD. After the delay time, again it will take some time to get the steady state. That is what we have obtained this current graph, where we saw that after TD also it requires some time to attain its steady state value. In addition to the intrinsic part of the MOSFET, we have also seen that the extrinsic part of the MOSFET, which is nothing but extrinsic capacitances and extrinsic resistances, governs the overall MOSFET operation. And hence it is very important when you are using this device in analog or digital circuit, you need to properly model the effect of extrinsic resistances and capacitances for proper operation. So we will stop here for today. Until then, take care.